Welcome to our project overview for Clemson University's Integrated System Design 2 course. Our team developed an IR drone aim trainer for under $400 with the goal of creating an affordable system for real-time aim training. This project was designed to measure user performance in real time using a drone-based targeting system. By combining embedded systems, wireless communication, and live data processing, it provides feedback such as accuracy, reaction time, and hit-to-miss performance. Our goal was to build a complete working prototype that could do more than simply detect a hit. We wanted it to collect useful data, support multiple game modes, and give the user clear, live feedback through a base station interface.
To do that, we used a Raspberry Pi Pico W microcontrollers for both the emitter and receiver, along with a Raspberry Pi 5 as the home base. These components work together to detect hits, transfer data wirelessly, and display results in real time. Next, we will take a closer look at each part of the system.
This is our drone aim training project. The goal of this project is to create wireless communication using infrared technology between our emitter and our receiver. This is the emitter of our project. What this does is it shoots infrared information to our receiver whenever we flick this button. Simultaneously, it also communicates wirelessly to our home base so that we know when every shot has been taken. Let me show you how it works. We have our battery, which is stored in the bottom of it. This is a little mock-up of it. We're able to convert what is nominally 7.4 volts down to 5.1, which is what our Raspberry Pico W likes. And from this Raspberry Pico, through a MOSFET, we're able to send the power to our LED that oscillates at 38 kilohertz. This is our receiver. It is mounted to our drone to act as a moving target. It works basically the same as our emitter with the same exact power electronics using the same exact microcontroller, the Pico W. How it works is there's a little infrared receiver right here that has a bandpass filter at 38 kilohertz. Because our emitter shoots at 38 kilohertz, so whenever this detects the correct sequence of information at 38 kilohertz in the infrared spectrum, it's able to determine that it's been hit, and then it will simultaneously send a wireless signal to our home base through the Wi-Fi that it has been hit. This is our home base. This is the communication and monitoring hub for our whole system. Inside of it, we have a Raspberry Pi 5 and a router that is all powered by this LiPo battery. What it does is it's able to communicate wirelessly with our emitter and our receiver. Once it gets that information, you're able to play some games. So we have 3 different game modes that you can play. One we call Beat the Gamecocks, which basically every time you hit the receiver, which I'll demonstrate just by touching the screen, one of the Gamecocks gets knocked unconscious and you win the game. For accuracy, it's just like the game Duck Hunt, where every time you hit a duck, you get 100%, but for every shot you miss, your accuracy goes down. And finally, you can get the reaction time, see how fast you are at shooting. I'm pretty slow at it. And ultimately, you can showcase your scores on the leaderboard and see who's the best at it between your friends if you want to do this as a fun game.
With those components in mind, this diagram shows how the full system comes together. It gives a complete view of the interaction between the emitter, receiver, wireless link, and base station. Before finalizing the design, we established a set of hardware requirements to guide development. These included infrared wavelength, modulation frequency, engagement range, telemetry range, latency, power consumption, drone weight, and expected flight time. These requirements shaped the design of the emitter circuit, receiver circuit, and home-based power system. Each section had to work reliably on its own while also fitting into the larger system without sacrificing portability or responsiveness.
In addition to the hardware goals, we also defined software requirements for communication speed and system responsiveness. These included packet rate, packet size, timestamp resolution, interface refresh rate, and reconnect time. This flowchart shows the overall software structure of the project. It maps how data moves through the system from hit detection at the hardware level to the live feedback shown to the user. For the graphical interface, we use Python with Pygame and Qt PySides 6. The result was a GUI with a main menu, leaderboard, and 3 game modes that allow the user to interact with the system and view performance results clearly. Our hardware development began by studying infrared systems already used in applications such as laser tag and remote controls. From there, we tested transmitter and receiver circuits on breadboards, refined the design through repeated trials, and then created a custom PCB for a cleaner and more reliable final build. On the software side, we programmed the embedded components in C and tested each section individually before integration. We then connected the hardware and GUI through a Python bridge file using TCP communication, allowing the system to display results in real time at the base station.
After integration and testing, the system performed as intended. The emitter, receiver, router, and the GUI were all able to communicate successfully, and the transmitter was capable of registering hits on the moving drone from distances of up to about 200 feet. The testing also showed that the project functioned well as a complete integrated system, not just as separate parts. It confirmed that the design could provide live feedback in a practical training environment while supporting multiple game modes and performance tracking. The following series of clips features some demonstrations of the design.
Game's over, you won.
Okay, that's fair. Yeah, you are.
Your own battery almost dead. Just keep saying hit till it misses. Is it hitting now?
Just be extremely accurate. Throughout development, we faced several challenges that shaped the final design. Some of the biggest included interferences from environmental infrared sources, supplying enough power for accurate transmission, maintaining communication between devices, and managing reduced drone flight time caused by added payload weight. Looking forward, there are several ways this project could be improved. Future additions could include autonomous drone movement, a mobile app for game control, extended multiplayer capability, and possibly moving from infrared to laser-based targeting for even greater precision.
Overall, the project achieved its main objective and resulted in a functional, low-cost training platform. The system performed especially well outdoors, and the base station successfully delivered live updates on metrics such as accuracy, reaction time, and hit count. These are the references that supported our design, development, and testing process. They provided technical background on infrared communication, embedded hardware, and the software tools used in the project. Thank you for watching.